first, the GPU. What is GPU? And as you can see, here is the structural difference between CPU and GPU. As you can see, the cache on CPU is much larger, and I don't know why I can see my mouse. Okay. As you can see, on GPU, the cache is very tiny, and the CPU architecture is optimized for low latency access to the cache memory. But for GPU, the architecture is optimized for the parallel computation. And as you can see on this plot, this is GPU and this is CPU. As you can see, here we have 4 tasks, and maybe have 4 tasks we want to run on CPU or GPU. And as you can see, CPU, as we look at each task, CPU is much faster, but GPU can, if we're only talking about one code, but CPU can only do it serially. But on GPU, we can do it in parallel, and even though each task take a little bit longer time, but overall, as you can see, it's still faster. And just as you know that more and more supercomputers relies on GPU parallelizations, and one example is Frontier, which is the fastest supercomputer in the world. Okay, in order to use these GPUs, you need to use some tools to run on the GPUs, and NVIDIA maintains the CUDA toolkit since 2006, and it's providing a development environment to program on GPU, and it provides multiple high-level programming like C, C++, Fortran, and Python, and so on. And also provides some high quality libraries like CUDA+, and so on. It also have some beautiful profiling and debugging tools, which will be really useful when you're trying to optimize your code. And here's a very simple draw about if you want to write a code which can be used on GPU. It contains 2 types of code: host code and device code, and it will have different decorator, host, device, or global. So the host code will be run on CPU, and because the GPU machine still have CPUs, it cannot, then the device code should have these decorated device or global, and you also need communications between the CPUs and GPUs in order to make it work. And here's a very simple example about how to write a GPU code. So here, basically, we want to do class operation about 2 arrays and get a new array. Basically, we need these 5 different steps. First, we need to initialize the data on CPU, then transfer the data to GPU, then GPU will do the class operation. Then we need to transfer back to the host and to print or write to disk and something. As you can, here's a real code. As you can see, first we allocate memory on the CPU and set up initialize the data, A array, B array on CPU. Then we use this so-called CUDA malloc to allocate memory on GPU. Then we copy the data from CPU to GPU and run this device function, which defined here, basically do the plus operation for these arrays. Then we copy back from the GPU to CPU and the print on the CPU. That's the basic idea how you can write a GPU code. And here's the output of this code. Okay, so next I want to talk about AsterX. So as you can see, we need a lot of this decorate and be careful about memory copy and from the GPU and the CPU. And but AsterX provide this software framework to user-friendly, such that you can coding on GPU, and it's a framework for massive parallel block structure at AMR applications, and it's developed by LBNL and REL and so on. And it's part of the Excel computing project. And it has the following key features, like it supports C++ and Fortran interface, and it supports both 1D, 2D, and 3D, and it supports natively the staggered grid, and so on. Yeah, and it also provides this lambda thing, which will make it easier to code instead of what we see before. And okay, then as to the GPU strategy, here's a comparison between the parallelization on using OpenMP in CPU and parallelization on GPU. As you can see, these two different large blocks represent the two MPI, and each MPI you can parallel using this OpenMP. And when you are trying to use OpenMP, you just divide into the large box into small boxes, but you can't have too many OpenMP thread on each node. So it divide in large blocks, but on GPU, basically you divide each MPI data into really small pieces, because you can have a lot of GPU thread on each node. So it will divide into these small cells and distribute to each thread and do a calculation and collect the data back. So yes. And AsterX basically have this strategy to keep the mesh and the particle data on the GPU as long as possible, because the movement between GPU and the CPU is expensive and slow. So yeah, we want to minimize this kind of operation. Okay, next, AsterX. AsterX is the new driver for the Cactus or Einstein Toolkit, next generation driver, and it is based on the AsterX framework we just talked about. And because of it based on this AsterX framework, it can have all the key features of AsterX, and yeah, and right now it provides the AMR based on local criteria, and basically on the grid. You can tell me where you want to refine grade, and it will refine. And we already mentioned this. And another feature I want to mention is the I/O. Now it's for the both Cyro and OpenPMD, and it's public, as you can check out on this link. And right now we have a few applications already. So the Vim2X basically show you how you can write a song which can use AsterX. And we also have a simplicity song which can evolve Einstein equation in vacuum. Not yeah. And involve Einstein equations, not necessarily vacuum. And or we just as you know, is already Graham Max, which is a new geometry code based on AsterX. And today we will talk about more about this new another new geometry code, AsterX. So basically, AsterX is a song which use the AsterX driver in Einstein Toolkit, and it is publicly available here. And right now, it's already implemented this flux, LLF and HLE. And for reconstruction method, we implemented the minimal PPM, ePPM, Windows 8, and P5. And for counterplaying, for both CPU and GPU case, we have 2D Noble and 1D Venezuela. But we also we can also use Weaponman, but right now it can only work on CPU version of the code. For the equation of state, right now it's only supported ideal fluid and polytropic. And later on, we want to implement the final temperature tabulated EOS. And for the factor potential evolution, we already implemented flux CT and doubling CT. Yes, that's pretty much about the AsterX. So next, I want to invite Lorenzo to talk about the difference between when you try and write a song for Copied and AsterX.
Thanks, Liwei. Yeah, so if you go to the Slack space, Liwei, sorry, can I open the Slack channel here? I put the link to this tutorial on the Slack space for the workshop for the school under here. Yeah, you can find the link on the tutorial discussions here. That's the link if you want to follow along. There's really not much to be done. There's really, can I close this? Go to the other, okay. Let me go. Yeah, that works. Is it okay? Can everybody? Bigger? Okay.
No. Oh, here. Okay.
Nice. Is that any better? Okay, I'll try to. Okay, I will explain. So it's fine. So in this notebook, I'll try to explain what's different when you want to move your Thor from using Carpet to using AsterX. Okay, I'll try to explain this with an actual example code, a piece of code taken from AsterX. This piece of code performs the initial primitive to conservative conversion of your evolution variables. All the pieces of code that I will show are taken from, the first one is the actual prim to con, so the primitive to conservative converter, and then there are other code snippets taken from other codes that are listed here. So just to get everyone on the same page, the primitive to conservative conversion is needed because, as most of the people here know, I'm sure, usually you want to cast your evolution equation into, in GRMHD, you want to cast your equations into flux conservative form. And the reason being, basically, there is a theorem that essentially states that if the numerical solution to a hyperbolic partial differential equation, which is cast in flux conservative form, converges to some function f with increasing spatial grid resolution, then that function f is a weak solution to your partial differential equation. That's why we want to cast our equation into this form. And as an example here, I'm showing the conservation equation for the Erasmus density, where you see that this variable d is your conserved variable, okay, and is essentially the density times the log factor, and then the term in the the divergence term contains what we call the flux associated with our conservative variable. And all those conservatives essentially are functions of the primitive variables, are computed from the primitive variables. Okay, I'm just gonna skim through this. So yeah, just to know what this piece of code is about. The point here is actually not that much about the physics or what we're going to do. It's about the syntax. Okay, so I'm going to jump to that section. So the first thing we want to do in our AsterX code, well, we want to include the usual Cactus header files. So cctk.h, arguments, cctk parameters. Then in this particular case, we include prim2con.hxx, which defines some structs and some routines which are useful here. But then most importantly, we want to include loopdevice.hxx, which contains, it's a carpetx header file, which contains all the infrastructure you need if you want to perform loop on a GPU. Okay, and you got to remember, you have to use the loop namespace, which you see here. Oh, sorry, you see here at the bottom. Then in this piece of code, we declared our schedule function, which is, as usual, a function of cctk arguments. So nothing changes from carpet. But then when you declare your cctk arguments, this is slightly different than with carpet. You have this cctk arguments x. So pay attention to this x. This is crucial. Okay, and must be included if you want all of your grid functions, everything to be well defined. So remember about this. And yeah, the usual declare cctk parameters doesn't change. Yes, in carpet you would have this instead, something like this, or just declare cctk arguments would work. Then this code, for each grid point, we want to build our conservative variables starting from the primitives. So we got a loop somehow over the grid. And the way this is done is quite different than with carpet, because here, basically a for loop wouldn't quite work. So we want this for loop to be executed on the GPU. The problem is we cannot run on the GPU directly, so to say. We need, as Liwei said before, we need a CPU to drive somehow the GPU. The CPU is usually referred to as the host, the GPU as the device. And basically, yeah, as Liwei said before, we want to include, if we want to make some function, a function which runs on the device, if we are working with, pure CUDA code, we would include this keyword global, which identifies a function which is called by the host, but then run on the device. And I point you to this link to the CUDA documentation for some further information. But yeah, in essence, as Liwei said, we have the manual steps. If we want to run CUDA code, it's a lot, because we have to manually allocate memory for all the variables that we need on the host via malloc or similar. And we need to manually allocate memory on the device with CUDA malloc. And then we have to manually copy the data from the host to the device, and then call the device function, and then again transfer back the data from the host to the device, free the memory on the host, free the memory on the device. So it's a lot. It rapidly gets clumsy and difficult and error prone as your code grows bigger and bigger. So yeah, CarpetX provides. So first of all, AMRX provides a useful wrappers around that simplify all this process, and then CarpetX provides additional wrappers around those AMRX wrappers that essentially make you able to loop efficiently on the device with let's say simple syntax. Okay, here what we are doing is we are launching a kernel, so the device function on the device, and this is basically what you would write in place of the usual for k equals 0, k lower than cctk lsh blah blah blah. In place of the usual carpet loop, you would write this, okay, to initiate your loop. And importantly, the same piece of code can, if you compile your code to run on GPUs, then you will launch a GPU kernel. But then if you only compile the code to run on CPUs, the same piece of code will run on CPUs as well. And you will just use OpenMP multi-threading, okay? So we have grid, which is an object which is declared. It's a grid desk-based device object. You can look it up in loopdevice.hxx. Loop int device. It's a method in that object, which basically says we want to loop over the interior of our grid. Okay, so don't loop over the ghost zones. And then there is this 111. 111, you could have any combinations of ones and zeros. Okay, 111, it means that our loop is going to be cell-centered. We're going to loop over the centers of each cell. 000 would mean we are looping over the vertices, and similarly, you can loop over the faces or over the edges by suitable combinations of ones and zeros, okay, which I've described in this line here. And then, okay, so this function takes the number of ghost zones as an argument, and the other argument is a C++ lambda, which the symbol here means that the lambda capture values by copy. And this is related to the fact that you need to copy data from the host to the device for your loop to function properly. So you cannot capture by reference. That would not work. Okay, so capture by copy. CCTK device is basically equivalent to the device CUDA keyword at the end of the day. So run on the device. you need to pass this object, which identifies this point descriptor, which identifies a point in your grid. The point descriptor object, let me see. Yeah, the point descriptor object, if you want to have a look at it, is a struct, and is defined in loop.hxx by carpetx. And it defines a variety of things that characterize a point. Okay, so you have a multi-index, unit vector in some particular direction. Okay, nearest interior point, a lot of things. Okay, as some deprecated stuff as well as of today. But basically, yeah, you just pass a point descriptor to your lambda. Okay, and that's the way you initiate your loop. Okay, we can just skim through this, and then you need to, well, okay, you initiate your loop, then you got to do something, right? So this is in the body. This something is in the body, inside the body of the lambda. In this particular case, what we want to do is, as I said, build the conservatives out of the primitives at each grid center, at each cell center. Okay. So for this to work, we first interpolate the metric which lives at the vertices. We interpolate it to the center, and this is done by this AsterX function, calculate average vertex to center. Okay. Is SMAT is an object representing a symmetric 3x3 symmetric matrix, and here is how calculate average vertex to center looks like, and it's a good way to see how we can actually access individual grid points if we have a grid function. Okay, so this function takes as an argument a GF3D2 object, which is essentially what was a grid function in Carpet. Okay, so GF is our grid function. We loop over the vertices of a cube, essentially, and we sum up the values of the vertices. And the way we access, you see here, P dot I is the GF P dot I accesses the value of your grid function at point P. Okay, and in this case, we access the point P dot I. P dot I would be okay. So let me start from the beginning. This was a cell-centered loop. Okay, we saw that above because it was the way we declared our loop. It's a cell-centered loop, 1, 1, 1. Okay, so P dot I identifies the center of each cell. Okay. Okay, so now from the center, essentially, we want to move a little bit to get the value of the grid functions in the neighboring cells. Okay, so this little di, little dj, little dk can either be 0 or 1, and depending on the direction, we get the grid function at different points. We sum it up, and then we take the average. That's what we do. So we finally have our the grid function here is the metric. So we call it on gxx, gxy, blah blah blah. So we have all of our components of the metric at the center of the cell, and from here we have a function that performs the primitive to conservative conversion. Okay, so it takes as input some values, this pv.row, pv.val, blah blah blah, which are initialized using the grid function values at the center of our cell. Okay. And prim to con will take this object primitive PV, the metric, and this other object conservatives, and it will fill the conservative object based on the primitives and the metric. Okay. And then once we have the CV object filled, we initialize the grid functions corresponding to the conservatives at this particular point using what we got from prim to con. Okay. And again, the way we access the grid function is by using this p.i object. Okay. Yeah. So if you were to write the same thing with carpet, you would do something along those lines, more or less. So you would do just the regular for loop, okay, over the three directions. Z, J, X, okay, that's the order, the convenient order to loop over your grid function because of the way they're stored in memory. Then you would need to get the index, okay, via the usual cactus macros. The index of this particular point, the neighboring points in all the neighboring points in different directions, and then here's when you perform the average, and so you would, yeah, that's the usual thing, right? Do something with your values. Okay. The main difference is then the way we loop and the way we access grid functions. That's the two main things in the syntax. So that's about it for the syntax. Of course, a Thorn also has all those CCL files that you need to provide, right? And there are some differences. They're not too deep. The carpet versus carpet X CCL files are not too different, but there are some important differences. First of all, in the schedule, you wanna, well, in all of your parameter files, carpet X parameter files, you wanna set the cactus presync mode in such a way as to recognize the reads and write directives that you put in your schedule when you schedule a grid function, a function. Okay, so for example, in our case, the routine prim to con initial that we saw above is scheduled like this. You see that you need to say which variables are read and which variables are written by this routine. Okay. And the reads and write directives are only recognized by Cactus if you set this parameter presync mode appropriately. So, for example, you could say, I don't know, mixed error or presync only, just to only recognize reads and writes and ignore all sync statements, for example. Okay. But it's important that reads and writes are correctly recognized. Do I do that? Mm-hmm. Thanks. Yeah, so this is how you schedule your routine. Or you have to say whether the grid functions are read or written in the interior or everywhere in the domain. So if, for example, here you see everywhere, you see interior, interior just skips the ghost points. Okay. And then finally, the interface is a little bit different. here's an example of how we declare the conservative variables related to the conserved momenta. Okay, you see that is a real grid function. It is a grid function. Okay, GF. That's the usual thing. But then we have to declare this centering that wasn't there in Carpet. And the reason is that AMRX, which CarpetX is based on, natively supports different centerings within your cell. Okay, so for example, this grid function is fully cell-centered, CCC. We could have said VVV to have it vertex-centered, or any combination of V's and C's would produce edge centering or face centering. Okay, that's one difference with Carpet. Another important difference is that you want to provide, so for a grid function like this one, which is to be evolved in time, you need to say what is the right-hand side related to that grid function. So when you call the method of lines, essentially operator, this grid function knows what the associated right-hand side is. Okay, and you do that at the level of the interface.ccl file. So this is different from the Carpet. From Carpet, in Carpet you needed to register method of lines, register evolved, register constrained, and all that. So you don't need to do that with CarpetX. So this is described in this section here. And the last thing I want to mention is this dependence keyword. So this means, maybe someone can correct me if I'm wrong, but I believe this means that once mom or any of the mom X, mom Y, or mom Z is updated, goes to the next time step, then all the dependents here are set, are made invalid, essentially, are poisoned, are set to none. I think that's what that means. And it's a safety feature that CarpetX added compared to Carpet. And that's about it. That's basically how you would port your Thorn from using Carpet to using CarpetX. I don't think there's much more to that. And yeah, thank you. And next, I want to leave the word to Jay with some examples on AsterX.
Someone speaking?
Yes. Oh, can somebody, can the online participants hear me now?
Yes, we can hear you now.
Oh, okay. And can you see the screen as well?
Yes. Yes.
Okay, so I'm sorry if I was muted earlier. Just to recap quickly, let me go back. So what we're gonna do is you go to your menu in your tutorial server, and then the first notebook you want to look at is CarpetX setup 1 to just quickly install CarpetX, build it in your server. And so this basically you just keep following these instructions here. You just execute these cells and try to untar the CarpetX tarball, and then basically again you try to get components and also have this par file that you can write. Well, it's not the tarn list, sorry. And then you go to the CarpetX folder and try to first do the setup that I think we talked about also during the cactus tutorial. And that sets up your sim factory settings. And then you may want to build your local CarpetX tarball, which also contains tarns from AsterX. So this basically showing that this is building the code.
It's doing nothing.
Yeah, it's already pre-compiled, right? So
Yes.
So
you really could skip that step if that last step if you wanted to.
Mm-hmm.
But let it finish. Since you started it.
Yeah. Okay.
It's going to take a while. It shouldn't take that long.
Yeah, these
it's just going to check the status of the thorns, really.
Yeah.
So I mean, it had to do from the Perl script and check the status of the thorns, but yeah, it should be reasonably fast.
Mm-hmm. Yeah.
So if I want to do this somewhere else, and without the tarball, you can just like give full CarpetX and then do the rest like instead of doing the untar.
That's right. So yeah, of course, if you're doing it on your local laptop, you need some prerequisite libraries that CarpetX requires. So once you have that installed, and then you might need some the config files for sim factory that you want to provide for your laptop. And once you have that, I think you can just follow these. You have these tarn lists available on the AsterX repository. You can use that. Yeah. But also in the future, if you have any problems, feel free to contact me or any of us, so we could help you out with that. Okay, so it's the final stages of building this executable. This takes a couple of minutes, maybe.
We can just open them.
Yeah, meanwhile, I can, till it builds and creates the executable, we could go to the other notebook that we could use to actually perform a simple simulation with AsterX. So the simplest case is this shock tube that we've talked about during the talk earlier. So you can go on that. Okay. Just to give you a brief background about what this test contains, it's a magnetized test, and where you have basically a you set up your domain and you have a discontinuity in the middle. So this discontinuity essentially is given by this initial data you set up for your primitive variables. So for instance, you have the density set as 1 for your left state, or and on the right state you is 0.125, and the velocities are set initially to 0 in both left and right states. And then you can also set up the initial magnetic field components, Vx, Vy, Vz. In this way, these are the initial data conditions that we take from these Balsara tests, which are standardized for any MHD or GMHD simulations, used to see how accurate and correctness of your code. So then we used the ideal gas equation of state with gamma equals to 2 for evolution, and this initial data is essentially provided by this thorn called AsterX seeds. And here you have the domain from minus 0.5 to 0.5 we use 200 grid points. And as boundary conditions, you just linearly extrapolate from the interior to your ghost zones. And here the contact discontinuity, as I said initially, is at x equals to 0. This is the shock is along x direction. Let me see if it's okay. So the executor was already meanwhile built. Again, we will just execute this magic cell and go back to this CarpetX repo. And let me quickly describe the par file that we use for such a simulation. So the number of tons we need for this is listed here. CarpetX, again, Liwei and Lorenzo talked about, is the driver and that we use. So we want that. And IOUtil essentially is used for input-output for actually outputting your data. And you have ODE solvers to do your Runge-Kutta steps or evolve your ODE in time. And you have timer reporter. It gives you some timing information, how your simulation is doing and things like that. And ADM base, what we recently was renamed to ADM base X, provides your metric variables and grid functions. And then Hydrobase X, now it's what's called, provides the hydro quantities. And you have TMU base giving you your TMU, essentially a special energy tensor. And we have AsterX, which I mentioned earlier, provides you the initial conditions for this this kind of a shock tube test. And you need the AsterX thorn, which is basically the geometry code that we have. And EOSX is the provider, driver or the provider of your equation of state. In this case, we use a very simple one, the idle gas one. And moving on, so this test is done in uniform grid. So we set the number of levels equals to 1, and we want 200 grid points. Is what we said. And here, as Lorenzo mentioned earlier, you have to set up your schedule. So if you want to see the output of your schedule, you can check this parameter to yes. And Cactus also now recent additions provide this setting called precinct mode. I think Lorenzo briefly mentioned this as well. And this is essentially helps you to make sure your reads and writes are correctly done. And if you have any errors while synchronization or some issues with your data, this would catch that and error out. And then next is essentially these Cactus parameters terminate and final time. What you want to set in your simulation is you're set to 0.4. And this is a simple chalk tube test. So the metric is basically Minkowski, and that's what we set here. And we don't want too much information coming out of carpet X, so we set the verbose parameters now. And these carpet X parameters set up your initial grid. That actually the extent of your grid. And then I mentioned earlier again, we apply in this case linear extrapolation as boundary conditions, both in your upper and lower boundary in all three directions. And here we've set this n cells parameter to 200 earlier. So these are the parameters from carpet X that are setting actually the number of grid points. So here you have 200 grid points along X, while you have only 2 along Y and Z. And then since this is a uniform grid simulation, we had earlier set n levels to 1. So this essentially tells carpet X that, okay, I just want my maximum number of refinement levels just as 1. And there is also a regrid parameter, but here, since we are doing a simulation in uniform grid, so we don't want to have any regridding to 2. So we just set to some random value here in the case of a very large one. There are other parameters for AMR that are called blocking factors, and this sets some criterion on how you want to evolve your AMR the cells to refine or de-refine as well, and in what way. So how many blocks do you want? So typically you set this to 4 or 8, but in this case, again, this is not used because we're doing a simulation in uniform grid. And the parameter that is used to checking if you want to refine or de-refine is called regrid error threshold. And you can pass this as a parameter here too, but again, this is a uniform grid simulation, so this is basically not doing anything. Then you have in carpet X different prolongation operators, and here you have different types. So let me quickly jump to the param.ccl of carpet X, which talks about these different parameter prolongation types. And in this case, you have different options to choose from. You can either interpolate between the data points, or you can conserve, or basically interpolating the cell averages. And the one we choose in this case is you interpolate the vertex-centered variables while you conserve the cell-centered ones. So you can play with that as well. And then the number of ghosts used in this case is 3, because we use high-order scheme called Rubino-Z, and the current factor in this case we set to 0.25. And here we specify from master seeds what test we want to perform. So this is a 1D test, and which test case is this? In this case, it's a Balsara 1 test, and the shock is along the X direction. And here again, the AsterX parameters are basically you specify the reconstruction method you want to use, the type of flux solver, and then the tolerance you want for your quantuplum scheme. In this case, is the noble quantuplum scheme that is used. But if there is a failure of the noble quantuplum scheme, then it fallbacks to the Valenzuela one. And this is the maximum number of iterations you want to set for your quantuplum to try to find the root before it says, oh, okay, I've given up, I haven't found the root yet. Then there is also something called a debug mode. So if there are some failures, AsterX will print out details of what failed, which parameter, if there was a failure in reconstruction or a quantuprim. So you can set that to yes or no. And there are some unit tests we've implemented both in the reconstruction thorn as well as the quantuprim thorn. So for this, in this case, if you want to print out some details of the unit tests that are if you set this to yes, the unit test will be performed before starting the simulation. And then for EOS X, you can specify what kind of EOS you will use to evolve the system. And here, GL gamma is basically the gas law gamma that you want to provide for this gas law, idle gas as EOS. And then polygamma is basically the polytropic gamma. So what AsterX does is it sets an atmosphere as well. So you could say, okay, provide this polytropic gamma, which is so atmosphere is set based on this polytropic equation state. In this case, of course, this is dummy because we fill the whole grid with a certain density that I told you about. So there is no atmosphere set typically. And again, there are some limits that you can provide in the simulation, how much I can allow for the maximum of density or maximum of the specific internal energy EPS to go to, otherwise, and it will error out if you pass this threshold. Again, here just I set it to a very high number. And OD solvers that we use in this case is Range-Kutta 4. And for input and out, for outputting the data, you can do it in different formats, as Lorenzo mentioned earlier. Here I output, you can specify the directory where you want to output your data into, and how often you want to output this data or save this data. And then you can do this in different forms. Here, this is the silo format. The silo format can be useful if you want to visualize your simulation in case you're on visit and similar platforms. And TSV is basically similar to the ASCII format that we have in Carpet. And we can also output the data in the open PMD format, and that's what's done here. And again, timer reporter gives you some timing data for a simulation. So once you have that, let's execute this cell as well to create this par file. And once we have the par file as well, we can try to submit this simulation using SimFactory, where you're using number of processes too, and this is done in open in pure MPI, so we set number of threads as 1. And here our wall time is set to 20 minutes, but probably the simulation will take less than 5 minutes to execute, hopefully even faster. And to follow what's happening, we can then execute the next cell to see what the output looks like in the spot. Maybe wait a couple of minutes. Okay, so it already started. Let me go to the beginning. So it tells you some data about what your working directory is, parameter file, etc., and what kind of pawns have been activated. And then you have some information on your, remember we set output schedule equals to yes, so we have some schedule information about where your different routines have been executed, different points like at initial or during evolution or post-initial, things like that. And won't go much into detail for this. It's quite similar to what we have in a Carpet simulation. And then we have this logo of CarpetX that's printed, that I think is very cool. And you have some information about some unit tests already being performed in different for different points. And like I said, this is just showing you an example of a unit test that has been done just before starting to evolve. So this is testing, say for instance, the counterprim. You pass in some initial primitive seeds, and then you try to see if do the counterprim and see if your seeds are matching with your output. And similarly, we do that for the Palenzuela case, and that's about it. This was the timer reporter data that we also have, for instance, in the Carpet simulations that you can use as well. And here you have details about, okay, your simulation has started, how much time it takes. For instance, iteration 0, this was initial time is 0, and how much runtime it took to actually begin this simulation. And it tells you, okay, it's what kind of variables are being written, etc., etc. And then you have, again, iteration 1, and so on and so forth. So let me see if simulation is already done. Okay, so took a couple of minutes, and we already have simulation running. Are people following this, and are they facing any problems with that, or no? All good up to now? Okay. So once you have your simulation done, we can try to visualize what kind of the data that we've stored. So just a quick recap of these, a quick number of steps to see how we can do that. Again, like I mentioned earlier, you have both, we save the data both in silo as well as OpenPMD formats. So we can go, let's go back to the home directory, and to visualize the movie, we use this package called Celluloid. So you might want to quickly install that. It should take maybe hopefully a minute or less than that. So for me, I had already installed it. So
Yeah, it's already installed on the server.
it's already installed on the server as well. So that's perfect. And you want to import some of the Python packages and provide the path for that. And then some libraries like NumPy, Matplotlib that you want to import. And since you want to see this animation in the notebook, we want to set that to notebook and not keep it online. And here you pass to OpenPMD the directory, the output directory, of the path to the output directory where your data is stored. So you execute that as well. And once, just to give you a quick brief of what this data contains for in the case of OpenPMD. So for each iteration, you have a number of records. And for each record, you have different components. And these components can be, for example, a 3D array. So in our case, so first, just to have an open dictionary, an empty dictionary, we define this variable, and to try to look into what we have in the data. We first here we want to print the iteration, and we create this dictionary variable. It's currently empty, and you want to flush or put all of the data that we have into this dictionary. This is just to tell you, visualize what or see what we actually have in the data files. And for instance, you have these records and components, so you can first read the different records that you have, and then again, this is again empty for now, and then you would flush the data in the next cell. So let me execute this cell as well. And this shows you, like for iteration 0, we saved the hydrobase BWEC, which is the Eulerian B, at level 00, and you have these 3 components of the magnetic field. Similarly, for specific internal energy, you have these saves and so on and so forth. And again, since we're outputting data every 10 iterations, then the second the data that is stored is for the iteration 10, and then again the multiples of 10. And this is what the empty dictionary shows, but then now you want to flush that information into this empty dictionary. So we have in there. And then you want to, so if you want to, for instance, in this case, you want to visualize the rest mass density, how it evolves in the simulation. So you choose the record you want to look at. In this case, is hydrobase row level at level 00, and then you specify the component. In this case, it's just hydrobase row. That's a grid function, and then you still have the features to plot this. So if you do that, you just get the snapshot. And I think at the final time, if you want to create the movie, we use the celluloid again package to create the animation. And that you can probably get. So you see that there is initially you have this discontinuity, and then your shock propagates along X. So that's what in this case. And if you want to clear some space on the server, you just want to probably delete your simulation directory. And that's pretty much it. And if you want to do a simulation in 2D or 3D, we have those notebooks ready as well. So you follow this, do the same game, and for instance, we quickly jump to the third 3D simulation here. So this is a TOV star, a magnetized TOV star, and we generate the initial data using the TOV solver that has been ported from Carpet to CarpetX. And these are some initial conditions that we define, like what kind of gamma you want to use for the polytropic equation of state, the kappa, and the initial central rest mass density. And then you are here in this case, we want, after generating the initial data from TOV solver, we put the magnetic field by hand using this AsterX tarn, and this is the prescription. These are purely colloidal fields, staying always just confined all inside the star itself. And then this is a very, very low resolution simulation, just so that this could actually work during the workshop. But of course, production runs use a very much higher resolution for such cases. So again, I'm going to quickly try to execute the different cells and try to run this simulation again. And I think I already tried this earlier, so you're following the output. So the final time I set in the simulation is about t equals to 400. Yeah, so it might take a couple of minutes for that to finish. So if you have any questions up to now, curiosities?
That's also no mesh refinement.
Also no mesh refinement, yeah. It's just I felt like it might be too much for the tutorial because we have a limited number of processors.
No, we don't.
Oh, you said
Try 10 on.
try.
We've got, no, we've got, there should be 3 compute nodes, each with 75 processors on them, I think. That should be way more than enough for this group, unless there's like 100 people online or something.
I see. I think you mentioned that we should use just 3 processors, so I kept the simulation very low resolution and uniform.
Yeah. No, I see. This is the thing, though. I didn't have a count for how many people were going to be here, so
right.
I knew there were going to be 100 people online.
Right.
But I think you don't have to worry about the number of processors today.
Oh, perfect. Mm-hmm.
So you can visualize the simulation data with IO and OpenPMD format, but the output in TSV format.
Yes.
What's that for?
So this is the same as ASCII. So if you want to check some data in 1D, if you have them
Like
out.
It's tab separated value.
Exactly. So yeah, so you can use that in glueplot and say visualize your maximum of evolution of the maximum rest mass density, things like that, to see what's happening there.
But do you not have to like specify output 1D?
Oh, in this case, I think you can do that as well. I'm not 100% sure. I think if it's you have that option in CarpetX to choose if you wanted to output 1D, 2D, or 3D. I think Eric added this feature recently. And if I'm not mistaken.
For all 3 formats that show it.
That I'm not sure. I think for TSV we have this feature. Yeah, we're not 100% sure.
You have to look at don't remember either.
So let's just wait a couple more minutes. I think it's close to. What's one thing that's interesting as well is let me. You see this here. No, I think it's using an older version of AsterX, slightly older. So here you can have some information also about how many grid updates per second you're doing, so you can try to understand how fast your simulation is and things like that. So I think here it's not so, the information is not printed in this case. I think the newer version.
It is from June, so.
Yeah, exactly. That's what I
So old.
Yes. Okay, it's almost there. All right, it's done. Like following the same steps also for visualization. I'm waiting for this to finish. Or what's taking long? Okay, there you go. And again, this case, I think Steve has already mentioned that Celeroid has been installed. So, and again, executing the other steps for. We go again to the create a dictionary, just show what kind of data again is stored here, and then we flush this into these arrays, and finally we try to get the theory. In this case, also we're plotting here the rest mass density, but just to visualize, this should create a movie. Let me try to show you here. I don't know if it's obvious here, but you can see that the star is kind of oscillating. You see the and these are basically the truncation errors at the surface that they propagate and then you cause these radial oscillations. Yep, that's pretty much it. You have any questions? All right. Thank you very much.